Hello there. I've created this primer on AI accuracy as I found there's a lot of materials online about this topic and people throwing around various metrics. And I found it all a bit impenetrable in the past. I mean, I thought I could explain it, then I tried to, got confused, read the materials again, and thought there must be a much more accessible way to think about this. Full disclosure, I'm not positioning myself as an expert in this matter, just somebody wanting to make the topic a little less opaque for as many people as possible. To begin with, one of the key things to consider is the accuracy trap. Accuracy is a very loaded word. You know, when we see 99% accuracy, naturally think, oh, wow, that's great. But what does that mean in practical terms? Does that 1% matter? And this is the accuracy trap. It's just like specifying a mean without standard deviation. It's missing important context that comes from other elements. If you read any AI ML books or do ML development in Python, you'll likely see a bunch of these metrics flying around. They'll typically be either shown as a figure from 0 to 1, which can be easily scaled to a percentage, or sometimes they'll do that step for you. But often when you see these, they may score very differently. For example, you may have a 99% accuracy, but only 90% precision, and an even lower MCC score. This can be confusing, and you may also ask, why do we need so many measurements? Well, we do in general, as each one of these tells a different story and can help us escape the accuracy trap. As a quick note, I'll be referring to positive and negative a lot in this talk. Don't confuse positive with the optimal outcome and negative with the detrimental outcome. In this case, positive is the thing we're trying to detect. If we get a positive reading for fraud, for example, or finding signs of cancer in a scan, negative means we have not detected this particular case. Okay, if you're watching this, I'm going to make an assumption that you've seen a confusion matrix before. But for those who don't know why it's called a confusion matrix, it's because you'll be confused when you see one. No, really, it's because it shows how often the model confuses different classes. These show the classifications of the cases in your data set. This doesn't have to be a binary classification, but it's the simplest one to illustrate for this talk. It shows both the correct and incorrect permutations, but not the probabilities of them, which we'll discuss later. So we have true positives, true negatives, meaning that we've accurately classified the thing in question. And then we have the false positives and the false negatives, meaning we have misclassified the outcome. And this is where a lot of the nuance lies, as real-world outcomes of false positives and false negatives can be wildly different depending on the context. Anyway, accuracy is pretty easy to calculate. You can put this in a spreadsheet in about 30 seconds. As another side note, though, if you have a model that's claiming 100% accuracy, this often means you've been over or underfitted without enough data or without enough data variation, with some data leakage or scenarios that are far too simplistic. This means that your 100% accurate model will probably fail spectacularly in live fire tests. Same goes for balanced classes. You know, they can happen, but they're less common than imbalanced classes, having the same number in the positive and the negative outcomes. And class balance really matters. You know, see, if you've got a perfectly balanced set of classes and 100% accuracy, you know you're in some kind of weird fever dream, because this almost never happens. Now, I'll take fraud detection as an example. It's fairly easy to grok. The classes will be unbalanced, and this is to be expected in the real world. True positives are fraudulent transactions, and the true negatives are the legit transactions, which is the class with 99% of the population. You'd hope this would be the case with banks. So if we create a false positive, I flag a legit transaction as fraudulent, that's obviously annoying, but it's not necessarily too bad. It brings down the accuracy a bit to 99.9%. Whoops. However, though, if we have instead of false negative, we let a fraudulent transaction go through, it's a bigger problem to clean up. Our accuracy doesn't change, though. One wrong in 1,011 classifications. Only if you look at it another way, that's 11 positives, one of which is misclassified, and that's proportionally much worse. To hammer the point home, if you have 99% valid transactions in the real world conditions and 1% are fraudulent, you can create a very simple function that claims it's classified and just return false. It would still be 99% accurate, yet not do anything to ever catch a single fraudulent transaction. I mean, it would perform and scale beautifully because it's just a function that returns false, and it wouldn't need a lot of testing. And that's the accuracy trap in a nutshell, because this is completely useless. Well, maybe the F1 score will help us. You see this one a lot in textbooks, and it's useful in some contexts and considers positive case performance. So you can see that the F1 scores dropped more than the accuracy did, as positive performance is worse, ignoring the true negatives. F1 is useful when you want a single score that balances precision and recall, but it treats false positives and false negatives as equally painful. In fraud, false negatives often hurt more, so we might prefer to recall heavy metrics like F-beta, or explicitly choose a threshold based on cost. But let's look at some other metrics which may help us along the way with this. Right, so let's add something that does care when we miss a positive outcome by looking at false negatives too. It's called recall, or sometimes sensitivity. As we can see here, with a false negative, our number drops to 90.9%, which is proportional to the positive cases we've attempted to classify. Now, not everything is about fraud, and some kind of classifiers may care more about false positives. Maybe if investigating that false positive is really costly, you'd want to know about that. So we'll call this one precision. As you can see now, we have no false positives. It's 100%. So we can say that we predict something as being positive, we're correct 100% of the time. And this is called the positive prediction value. If we introduce a false positive, we can see that precision drops to 90.9%, showing that our positive prediction value is lower than before. There are a couple more, things like specificity and negative prediction value, as well as some other esoteric combinations which are geared to negative rates. I'm not going to go into all of those today, and they tend to get used less in general machine learning discussions. But there are a couple of other things I'd like to quickly cover. The first is the ROC-AUC, or the Receiver Operating Characteristic Area Under the Curve. Unlike the other metrics, which take classification, the Receiver Operating Characteristic looks at the probabilities for each classification. And when you have a score, probability, how well do those positives rank above the negatives across the thresholds? In the case of distinct probabilities of 1, the area under the curve should be 100%. In the case where it ends up being 0.5, that's basically no better than random chance of flipping a coin. This measurement gives you a good idea of how distinct things are in your classifier, which the confusion matrix explicitly does not show. And this is important to understand. However, for very rare positives, people also look at the precision recall curve, or the PRAUC, because the ROC can look flattering when negatives dominate. We won't cover all of this today. And finally, there's another accuracy-like metric that may be worth your time, the Matthews Correlation Coefficient, or MCC. MCC is basically a correlation between predictions and truth. It uses all 4 boxes and behaves well when the classes are in balance. Now, I'm going to show you the formula. It's not awfully complex, but it's more complex than the rest of them so far. So brace yourselves. Yes, it's a bit more involved, but thankfully in Python, you can just call the function and use it in your evaluations. It's quite interesting to see how often something that shows really high accuracy also shows a fairly low MCC score. So I'd prefer to use this. So let's quickly recap over everything we've covered today. Accuracy first. Use it when your classes are roughly balanced, and when things like false positives and false negatives have a similar cost. Don't trust when you have strong imbalances, or because you can always be accurate by predicting the majority class. Then there's the F1 score. How good is the positive class performance overall, the precision recall trade-off? So this is slightly better than accuracy in some cases. Then there's precision. Basically, this is the positive prediction value. When I say positive, how often am I right? When false positives are expensive, things like security alerts and automatic moderation. There's a negative prediction value, the flip side of precision. When I say negative, how often am I right? When you need like a confidence in things being all clear. There's recall and stroke sensitivity. This is the true positive rate. Of the real positives, how many did I catch? Used when false negatives are expensive, things like fraud detection, cancer screening, and safety monitoring. The specificity, or the true negative rate. Of the real negatives, how many did I correctly dismiss? Used when false alarms are costly and negatives dominate, things like diagnostics when people are healthy. And then there's the Receiver Operating Characteristic Area under the curve. How separate are your classes? So across all possible thresholds, how well does the model separate those two classes, which can be important? Then there's the Matthews Correlation Coefficient. If stakeholders want 1 score and the data is imbalanced, this is probably safer than giving a raw accuracy or F1 score alone. Anyway, that's been my little AI ML metrics primer. I hope it's been useful for you. I've been classified as Jeff Watkins. You, however, have not. Bye-bye.